Presenting unbiased gradient estimation in unrolled computation graphs with persistent evolution strategies. This is joint work with Luke Metz and Joshua Zoldigstein. So for the problem setup, consider a dynamical system with a state st at time t, whose evolution is governed by some parameters theta. On the left, we see an example of an unrolled computation graph for such a dynamical system, where at every time step t, we have a loss, L sub t, that depends on the state at that time step, S sub t. We define the overall objective to be the sum of these per time step losses. Many applications in machine learning give rise to such unrolled computation graphs, including RNN training, hyperparameter optimization, training learned optimizers, and reinforcement learning. On the right, we show what the state and the parameters correspond to in each of these applications. Classic approaches to learning the parameters in unrolled computation graphs include backpropagation through time, truncated backprop through time, real-time recurrent learning, and approximations to RTRL. However, most of these approaches suffer from truncation bias, high variance gradients, slow updates, or have high memory usage. Another issue to keep in mind when optimizing parameters in unrolled computation graphs is that long unrolls can lead to chaotic or poorly conditioned loss landscapes, in particular for unrolled optimization. So this was observed by Metz et al. In ICML 2019, and this visualization from their paper shows a meta-loss landscape for different unroll lengths. And we can see that for longer unrolls, the meta-loss landscape becomes chaotic and develops near discontinuities, which makes optimization challenging, especially for gradient-based methods. So one solution is to consider optimizing a Gaussian smooth version of the meta-objective. And evolution strategies, or ES, is a method for estimating the gradient of such a Gaussian smooth meta-objective. On the bottom right, we can see the vanilla ES gradient estimator, which samples perturbations epsilon to the parameters theta to compute a stochastic finite difference estimate of the gradient. So what are the pros and cons of evolution strategies? ES optimizes a Gaussian smooth loss surface, which overcomes chaos from long unrolls. It doesn't require backprop, so we don't need to store intermediate states in memory, which can be memory efficient. It can optimize arbitrary black box functions, including non-differentiable objectives like accuracy rather than loss, and is highly scalable on parallel compute. So in principle, using ES on full unrolls of the computation graph would work well, but it would be computationally expensive because we would have to do a full unroll for each parameter update. So we could only have infrequent updates. And in practice, ES is applied to truncated unrolls, which leads to truncation bias, similarly to truncated backprop through time. So next I'll introduce our approach, persistent evolution strategies, or PES. So at a high level, PES splits the computation graph into a series of truncated unrolls and performs an ES-style parameter update after each unroll. But crucially, we eliminate bias from these truncations by accumulating correction terms over the full sequence of unrolls. So PES is unbiased and allows for more frequent parameter updates. It also inherits useful properties from ES, including low memory usage, because again, we don't need to store intermediate states for backprop, and loss surface smoothing, which is useful for these chaotic loss surfaces that result from unrolled computations. So next, I'll sketch out the derivation of the PES estimator. And the first step is to consider a shift in notation. So unrolled computation graphs depend on shared parameters theta at every time step, as shown on the left. But now, in order to account for how the applications of theta contribute to the overall gradient, we're going to use subscripts to distinguish between applications of theta at different time steps, shown on the right. So instead of considering the loss at step t as a function of the state at step t, st, we're going to consider the loss at step t as a function explicitly of the entire sequence of thetas that have led to that state. So instead of L3 of S3 on the left, we're going to have L3 of theta 1, theta 2, theta 3 on the right. We're also going to define a matrix, capital theta, whose rows are the thetas at every time step. So next, in order to derive the PES gradient estimate, we note that the desired gradient, which is on the left of the top expression, the gradient of the loss with respect to theta, can be expressed in terms of the gradient of the loss with respect to the vectorized capital theta matrix, which consists of all of the per time step thetas. We'll see how this Kronecker product expression works in a minute, but knowing that this expression holds, we can estimate the gradient, the full gradient with respect to the capital theta matrix using ES, shown on the right. And this gives us the PES gradient estimator. So to understand how this expression works, in particular the Kronecker product, we can look at a concrete example with two-dimensional theta and 3 time steps. So here the matrix capital theta has 3 rows corresponding to the 3 applications of theta over time, shown on the left. And if we look at the vectorized form of the matrix capital theta and the full gradient of the loss with respect to the vectorized capital theta, those are shown on the right. We also show the Kronecker product of the identity matrix and the row vector of 1s for this particular problem on the right. And if we just carry out the product of this Kronecker term and the full gradient with respect to the vectorized capital theta, we see that this yields the desired gradient in the bottom right. So hopefully this helps to illustrate the shapes of the quantities involved in this derivation. Next, we'll see how PES decomposes into a sum of sequential gradient estimates. So here, bold epsilon is a matrix whose rows are the per time step perturbations. So bold epsilon has the same shape as the capital theta matrix. So first, we'll push the Kronecker term into the expectation. And then we note that the product of this Kronecker term and the vectorized matrix of perturbations is equal to the sum of the perturbations over time. We can further push this sum of perturbations over time into the inner sum over the LTs in order to obtain a sum of sequential gradient estimates using this psi sub t term, which we define to be the sum of the perturbations from step 1 to step small t. So now from the last expression, we see that we can obtain unbiased gradient estimates from partial unrolls by not resetting the particles between unrolls and by accumulating the perturbations that each particle has experienced over multiple unrolls, where this perturbation accumulation is done by the psi sub t. So we can estimate this last expectation using either a standard Monte Carlo estimate, shown in the bottom left, or what we do in practice is use antithetic sampling, shown in the bottom right, where we sample pairs of positive and negative perturbations at every time step. So next, we can look at how the ES algorithm compares to PES. So on the left, we see truncated evolution strategies, and on the right, PES, with the differences highlighted in purple. So first we'll look at ES. We're given some initial state, S naught, truncation length k, a number of particles n, and a standard deviation for the perturbations sigma, and a learning rate alpha. So in every iteration, we have a loop over the n particles, and in each iteration of this loop over n particles, we sample a perturbation epsilon. We run an unroll for k steps using the perturbed parameters theta plus epsilon to get a loss for that unroll. And then we use the product of the perturbation at that step and the loss from the unroll to build our ES gradient estimate. Now looking at PES on the right, we now initialize n copies of our state for the n particles that we're going to be evolving over time from their previous states. We also initialize a perturbation accumulator for each of the n particles. And similarly, we loop over the n particles, we draw a perturbation for each particle. Then we unroll now from the state for that particle with the perturbed parameters theta plus epsilon for k steps. Now the unroll gives us a loss for the unroll as well as the updated state. Then we add the current perturbation to our perturbation accumulator, psi I, and then we use the perturbation accumulator times the loss from the unroll to build our PES gradient estimate. So these are the only differences that need to be implemented. We can actually look at an example implementation of the PES estimator in JAX. And this is very similar to the pseudocode we just saw. So the first 3 lines of code here generate the antithetic perturbations. And then the next line of code uses JAX VMAP to perform all of the unrolls for all the particles using the perturbed parameters theta in parallel. So here we just avoid any explicit for loops. Then we add the current perturbations to our perturbation accumulators, again for all particles in parallel. And then we use the perturbation accumulator to compute our PES gradient estimate. So very similar to the pseudocode. Next, we look at the variance of the PES gradient estimate, which depends on the correlation between the gradients at each unroll. So we consider several possible scenarios, and we measure these variances using a tiny LSTM on both synthetic and real data from PenTreeBank. And we deal in each case with a fixed sequence of length 1000, which we split into different numbers of truncated unrolls. So for the first scenario, if we assume that the gradients for each unroll are IID, then the variance scales linearly in the number of unrolls. For the second scenario, if we assume that the gradients from each unroll are identical to each other, then variance actually scales as big O of constant plus a constant over the number of unrolls. So in the second scenario, we see that increasing the number of unrolls can actually reduce variance. And in the third scenario, with real data, we see characteristics of both of these two synthetic scenarios. So increasing the number of unrolls first leads to a slight decrease in variance, followed by a linear increase in variance. So next, I'll go over the PS experiments, which aim to demonstrate first that PS is unbiased, which allows it to converge to correct solutions that are not found by truncated backprop through time or truncated ES, that the loss surface smoothing induced by PS is useful for meta-optimization, and that PS can target non-differentiable objectives like validation accuracy. We're going to apply PS to several illustrative scenarios, including hyperparameter optimization, meta-training a learned optimizer, and learning a policy for a continuous control task. So first, we look at a synthetic influence balancing task that was introduced by Talek et al. In 2017, which is designed to have arbitrarily long-term dependencies. Here, the task is to learn a scalar parameter that has a positive influence in the short term, but a negative influence in the long term. And this task was specifically designed to such that truncated algorithms like truncated backprop through time will fail because the parameter will explode in the wrong direction. And we can see on the right that if we do apply truncated backprop through time with truncations of length 1 and 10, the parameter indeed is adapted in the wrong direction and the loss actually increases. Whereas if we use truncated backprop through time with truncation length 100, the parameter moves in the right direction and decreases the loss. We see that evolution strategies, vanilla ES, moves in basically identical fashion to truncated backprop through time, given the same unroll length, while PES in cyan performs very similarly to exact RTRL, which is the dashed black line, which is ideal in this situation. So next, we looked at a simple hyperparameter optimization problem on a toy 2D regression task, which has only one global minimum, but many local minima to which truncated methods could converge. So the task here is to learn a linearly decaying learning rate schedule, where we want to learn the initial and the final learning rates, parameterized in log space. And in the bottom left, we see the meta loss surface for this task, where darker is better. And we see that this meta loss surface also exhibits chaotic regions. And all of the gradient-based methods that we applied here, truncated backprop through time, UORO, and RTRL, all got stuck at the very start of this chaotic region, whereas vanilla ES and PES moved smoothly past this chaotic region. However, vanilla ES got stuck in a suboptimal region due to truncation bias, whereas PES converged to the optimal region. And on the right, we see the meta-objective values achieved over time by each of these methods. Next, we looked at a more real-world task with an MNIST learning rate schedule. So we wanted to meta-learn a learning rate schedule for an MLP on MNIST, where we learned the initial learning rate and decay factor in this case. And here, the full inner problem length was 5,000 steps. We ran both ES and PES with two different truncation lengths, 10 and 100. And we tried targeting both the training loss as well as the validation accuracy. That's on the right. So we see that in both cases, PES with both truncation lengths 10 and 100 converges to the optimal region, whereas ES suffers from truncation bias and converges to a suboptimal region. And on the right, we see that we are able to target validation accuracy, which is a non-differentiable objective, and PES works similarly well to targeting the training loss. We can also tune many hyperparameters. Here we're tuning a separate learning rate and momentum coefficient for each weight matrix and bias vector of a 4-layer MLP on MNIST. So here we have 20 hyperparameters, and we're comparing PES to truncated ES as well as random search for 4 different random seeds each. And we see that PES outperforms both truncated ES and random search with less compute. So ES also performs particularly poorly here because it moves in the wrong direction. We can also use PES to train learned optimizers. Here we meta-train an MLP-based learned optimizer, similar to Metz et al. 2019. And this learned optimizer is used to train an MLP on CIFAR 10. And because PES is unbiased, we see that it both achieves lower losses and is also more consistent across random initializations of this learned optimizer than ES. Finally, we used PES to learn a policy for a continuous control problem using partial unrolls. Here we used the swimmer v2 task from Mojoko, And we found that PES is more efficient than ES applied to full episodes in terms of the total number of environment steps we needed to take, while truncated ES failed completely due to bias. So in conclusion, PES is algorithmically an easy-to-implement modification of ES, which provides unbiased gradient estimates from partial unrolls. It inherits useful characteristics from ES, such as easy parallelizability, the ability to work with non-differentiable functions, and meta-loss surface smoothing. And PES has tractable compute and memory cost. And we've shown that it can be applied to various unrolled problems, such as hyperparameter optimization, training learn optimizers, and reinforcement learning. Thank you.